The same BM25 query can rank differently when rare terms live on uneven shards. Elasticsearch DFS search gathers global term statistics, so relevance stops depending on shard local counts. After this, you'll understand how to assemble a pipeline that ranks documents with shared scoring evidence and reports the added delay. I'm Professor Pi, teaching search and IR with simple Python. Cross-shard BM25 scoring is a real, practical stat once your index splits across shards or indices. If a rare term shows up only on one shard, that shard will compute term and document frequencies differently than the others. The result: identical documents can end up with different BM25 score values. That breaks predictable ranking and can mess up later filtering or re-ranking. Elasticsearch's DFS search fixes this by making those frequencies global before scoring. At a high level, DFS adds one fast extra round trip to collect term stats from every shard. Normal distributed scoring uses each shard's local numbers and then merges hits. DFS instead asks every shard for term frequencies and document counts, aggregates those global stats, and then asks shards to score with the unified numbers. The benefit is consistent, shard-independent BM25 scores. The trade-off is the small extra latency from that extra phase. We'll prove the trade-off with a compact experiment. Create two tiny one-shard indices, put the same matching text on both, but add extra non-matching documents to one index so local stats diverge. Then run the same query twice, once with the default query then fetch, and once with DFS query then fetch. We'll read the returned underscore values and time both searches so you can see the relevance fix and the latency cost side by side. Quick note: this code is designed to teach the core idea clearly. Library versions and local setups can vary, so check the official docs if your setup behaves differently. First, make sure the Python client can actually reach your local cluster before we try anything else. This snippet checks that the Elasticsearch Python client can reach the local cluster. Before comparing scoring modes, the search code needs a real Elasticsearch service behind the client object, not an in-memory stand-in. Elasticsearch http://localhost 9200 creates the official client, and client.ping gives a quick connectivity signal without creating indices or running queries. That keeps the first step intentionally small and easy to diagnose. The visible output shows whether Elasticsearch is reachable before we build the BM25 experiment. If ping fails, you stop and fix the local node rather than chasing a subtle scoring issue. With connectivity confirmed, the next move is to create the tiny uneven corpus that produces the shard local mismatch. This example creates the uneven shard distribution that makes local BM25 statistics misleading. The Elasticsearch Python client uses client.indices.create to make two one-shard indices. So searching BM25 star crosses two shards with different local collections. Both S1 and B1 contain the same query evidence, zebra. But BM25 big also has several non-matching documents. Client.index writes the tiny corpus, and client.indices.refresh makes it searchable immediately for the next step. The visible output confirms the corpus size that will drive the scoring comparison. This setup isolates the effect: identical matching text on different shard backgrounds. Now that the corpus exists, run a normal distributed search and watch the scores diverge. This code exposes the relevance failure caused by shard local term statistics. The query asks for zebra, and client.search runs with search type query then fetch, the normal distributed search style. Elasticsearch scores each shard using that shard's own document and term frequencies, before the coordinating node merges hits. Because S1 and B1 live in different one-shard indices with different local backgrounds, their identical text can receive different underscore values. The visible output shows the score gap, which is the inconsistency we want DFS to reduce. Seeing that gap makes the later comparison meaningful. To show the fix, rerun the same query while forcing Elasticsearch to gather global frequencies first. This snippet reruns the same Elasticsearch query with search type equals DFS query, then fetch. The important change is that Elasticsearch performs an extra distributed frequency step before scoring. So the matching shards use global term and document frequencies instead of only local shard statistics. The input corpus and query stay unchanged, which makes the comparison clean. DFS scores reads the returned underscore values for the same two matching documents and calculates DFS gap. The visible output shows whether global statistics removed the artificial score split between identical BM25 evidence. If scores line up, DFS did its job. Finally, measure the practical cost so you can weigh improved relevance against added latency. This example turns the DFS choice into a small engineering trade-off measurement. Latency times the same client.search call while swapping only the search type, so the comparison stays focused on the extra DFS phase. Taking the minimum of 5 runs reduces some local timing noise without hiding that real latency depends on cluster size, shard count, and load. Score fix carries forward the relevance benefit, while cost MS estimates the added response time for this tiny setup. The visible output puts relevance gain and latency cost on the same line, which is the baseline decision you can repeat on production-like queries. In a real deployment, this maps directly to 2 decisions. If you have a few shards and queries where rare terms matter, enable DFS for those queries. If you run a very large cluster and latency is tight, consider selective DFS only for certain query types, or use a 2-stage pipeline with a fast approximate pass and a DFS-backed rerank. What we learned: BM25 uses term frequency and inverse document frequency and can be inconsistent across shards when stats are local. Use Elasticsearch DFS search to collect global term stats, so identical evidence scores consistently. Remember one caveat: DFS adds an extra phase, and so increases latency, sometimes noticeably depending on cluster size. To extend this exact example, tune BM25 K1B on a larger product catalog and repeat the DFS versus non-DFS comparison while measuring NDCG. That will show whether the relevance benefit holds under realistic document counts and user queries. If short, practical IR helps, subscribe and watch the IR videos.